This is a short 5-minute summary video overviewing the details of a paper that I published early in 2018 looking at prediction of forces, in particular drag forces, on a nanoparticle trapped within a channel at transitional Knudsen numbers. It was a computational approach based on the solution of the Boltzmann-BGK equation using a discontinuous Taylor-Galerkin discretization scheme. So the geometry under consideration was a two-dimensional particle. So all of the work in this paper is based on a two-dimensional study of a channel about 20 nanometers in length, of width about 8 nanometers, with a 2 nanometer diameter particle in the center. And because of the small length scales involved, the Knudsen number of this problem, that is the mean free path of molecules normalized by the length scale, which in this case was based on the particle diameter, were all in the transitional region where the Navier-Stokes equations, the validity of the Navier-Stokes equations is starting to be questioned, and we need to compare that with a molecular approach. So the governing equation for all of this work was the Boltzmann-BGK equation. So that's the BGK approximation to the full Boltzmann equation, where the right-hand side molecular collision term is replaced by a simplification, which is based on the idea that the effect of molecular collisions is to force a non-equilibrium molecular distribution function, that's F in this equation, is forced to the Maxwellian equilibrium form F naught at a rate proportional to the molecular collision frequency. The discretization of the space of the problem, the spatial discretization, has two parts: the physical space of the problem, and then the velocity space, which is the potential velocities, which describes the potential velocities that molecules can travel at. An assembly of discontinuous triangles was used to discretize the physical space. So each triangle has 3 independent nodes, and where vertices of triangles combine, a weighted average of the values at the vertices is used for kind of post-processing purposes. And the velocity space is, which in principle is infinite in extent, is limited to a circle of radius, several thermal molecular velocities. That circular space then is mapped into a quadrilateral element in the eta zeta space, and the eta direction is discretized using a Labato quadrature method, and the zeta direction an equal weighting, equal spacing discretization approach. The reasoning for that is explained in the paper. So that's how the space is discretized. The equation, then, the numerics are based on a 2-step Taylor-Galerkin approach. In step 1, at the physical space cell level, half-time step fluxes are computed using a Taylor expansion approximation. And in the second step, a Galerkin weighted residual approach is used to work out the solution increments at each node in physical space based on the fluxes that were computed at the half-time step in step 1. And this results in a second-order scheme both in time and space. In terms of boundary conditions, the full details, of course, are in the paper. The most interesting one is how we deal with walls. So we assume that a proportion of molecules, a fraction alpha, are absorbed into the wall and remitted from the wall with the wall properties, that is the wall temperature. And the remaining fraction are simply specularly reflected off the wall, and you can use that assumption to compute your reflected molecular distribution function. And in fact, one of the things that we do in the paper is look at the influence of the alpha parameter, this assumption about the percentage of molecules absorbed into the wall on the results. So this is the physical space mesh that's used, about 30,000 cells. Of course, each of these cells has 3 independent nodes, so they're getting on for 90,000 independent nodes in this physical space mesh, which comprises 12 layers of boundary layer grid, so quasi-structured boundary layer grid. Here are the simulation parameters that we use, so at a range of alpha, that is wall absorption parameter, the gas methane was simulated because there were other studies in the literature using methane on this geometric case. And that's a number of 0.0214, and a range of Reynolds number cases were simulated, and the drag coefficient of the nanoparticle predicted. Our results were compared with a molecular dynamics approach in the literature and a continuum slip approach, a wall slip approach based on Navier-Stokes solutions. And the results that we got sat well within the kind of range of predictions that people are making for this type of flow. So if you want more details, the full paper is Nanoparticle Drag Prediction at Low Reynolds Number using a direct Boltzmann-BGK solution approach, and it's published in the Journal of Computational Physics 2018.